So this video will be covering the second law of thermodynamics, and by the end, we want to try to predict if a situation is going to be spontaneous or not by applying the second law of thermodynamics. So, in our previous video, we went over this concept of randomness, and we came up with the conclusion that since a state of more disorder is more probable, then that's the way things tend to go, actually. So, for example, if you flick a deck of cards, so you shuffle up a deck of cards and they're all out of order, okay, and then you just stand there and you flick the deck of cards, there's there's one possibility that they'll all land in order. Okay, but that possibility is so low compared to the number of possibilities that they land out of order that it's essentially not observed. So we say that the randomness of the universe is always increasing, and this it's called entropy, and the symbol for it is called delta S, or change in entropy. Okay, so and that this is the most plain way to state the second law. The entropy of the universe is always increasing. Okay, and we can actually quantify this value because we know we can define the universe as the system and its surroundings. Okay, by delta S, delta S cis and delta S sur. So one little side note about delta S cis: this is actually in textbooks. They never write when textbooks are referring to the entropy of the system. They omit the subscript, which is really important distinction to make because it could be confusing if you're reading it and you start confusing system with surroundings. So watch out for the text because they'll call it this. They'll write delta S and they'll use a little degree symbol. That means it's measured. This involves like the third law. If you call the entropy of a perfect crystal, if you set that equal to 0, you could actually measure individual molecules or atoms. You could actually measure their entropy or their amount of disorder. And if it's done at 25 degrees, it actually falls into a table. So if you see that, they're referring to the system. If you don't see anything there, okay. So if there's nothing there, okay, or if you just see S with a degree symbol, okay. So S means it was measured, but not the change in, and then change in means final minus initial state. So some chemical process has happened, and then you get the change in entropy. Okay, this one is interesting. We're going to be dedicating a lot of this video to this, the entropy of the surroundings. But if you add both of these, the system and the surroundings, then you have the entropy of the universe. So, for example, if you have like if you burn some methane gas, okay, in oxygen, okay, the system is going to be the chemical equation. Okay, and then the surroundings, this is known to be exothermic, this process. So this gives off heat. Okay, so we have the system. I'll put a circle around there, and then you have the surroundings, which is everything else. This is all the surroundings. Since we know that this is exo, this is actually going to heat up or release. So all the molecules in the air are going to vibrate more. Since we know that it's exo, it's releasing heat, then we know that since it's heating up, it's actually going to increase the entropy of the surroundings. So this is an interesting concept because what this allows us to do is if we know that the enthalpy, if it's exothermic or endothermic, if we know it's enthalpy, the system, we could actually predict the sign of the entropy of the surroundings if we know the enthalpy of the system. So what this allows us to do is put both of these in terms of the system. So we'll be rewriting this part of the expression in the video actually in the next slide. So what does all this allow us to do? So the first, second, and third laws, they allow us to answer some fundamental questions about chemical processes. So why does a change occur? And how much energy do I need to supply to make a non-spontaneous change occur? So, and all we really need to do is look at the entropy of the system and the entropy of the surroundings. And as I was pointing out, the entropy of the surroundings is if you know the temperature, is directly related to the enthalpy of the system. So this is related to the enthalpy of the system. So if we look at those two things, we can figure out if a change will occur. And if it doesn't occur, so if this is not a positive, if this value here, if this is not a positive value, what we just figured out, so if you get a negative value, so if you get a negative kilojoule value here, then what you just figured out is how much energy it takes. What you just figured out is how much energy it takes to get that process to work, to happen. Okay, so if it's positive, it'll happen on its own. If you calculate a negative value using this formula, then what you just figured out is how much energy it takes to get that process to happen. So this is super, super useful. Okay, so let's look and see how this works. Let's look and apply it to some different situations in this video. Okay, so the entropy of the surroundings is determined by the enthalpy of the reaction, which is what I was stating a second ago. So I'm gonna color this here and then match it up with what I'm saying right here. Okay, so this is defined as, this term right here is actually equal to delta S Sir is actually equal to the enthalpy of the reaction divided by the temperature. And you actually need to put a little negative here in front of the enthalpy so that because this right here is for the system and this right here is for the surroundings. But if you put that negative there, it changes it to be for the surroundings. You change the perspective of the enthalpy to be in terms of the surroundings when you put that negative there. So this leads to two results. One, if your reaction is exothermic, then the sign for delta H reaction is negative. Then this means if you put a negative here, it means the entropy of the surroundings is increasing. So delta S Sir is increasing. So this is the example I just was saying. If you burn something, then it's causing, so let's say we have a campfire. Okay, and then there's some logs here, and then these logs are on fire. Okay, then this is releasing heat into the surroundings. Just a second, I changed my slide for a second. So it releases heat into the surroundings. Okay, and it's going to cause all the molecules of air to start vibrating more and moving more. And this will increase the amount of disorder in the surroundings if you have an exothermic reaction. Okay, so if you have an endothermic reaction, if delta H RXN is endothermic, then the sign of delta H RXN is positive. Okay, then if this happens, if you put a positive number, so if you put a positive number, then your entropy of the surroundings is getting more ordered, is negative or more ordered. So if these are, if you have, let's say a lot of dissolving processes can be endothermic. So let's say you have a beaker, okay, and then you add, actually dissolving a sodium chloride actually takes in heat from the water. Okay, and then the water actually feels colder because they're losing heat. And when things get colder, they tend to get more ordered when they get colder because they're slowing down. They tend to get closer together. More IMFs are happening, so they end up getting more ordered if that happens. Okay, so But what would be driving that process? Why does that happen spontaneously when you add salt to water? Why does that happen spontaneously? It's because of this. This actually overcomes the fact that more order was created by the surroundings. It's that there's more disorder of the sodium chloride crystal because it was a lattice and now it's dissolved in water. So there's more mixing. So mixing actually increases the entropy of the system. So there's basically for the system, the entropy of the system, there's basically four ways you can tell. Okay, actually there's the best way to do it is you calculate it. You use a table. Okay, use a table and calculate it, which we'll go over in another video. So use a table and you calculate the value. Okay, and if you see it's positive or negative. It's based on the third law, which creates a reference point to be able to measure entropy. Okay, but without a table, there's several ways you can tell. There's four ways to tell. One of those ways is kind of not, it's not super reliable, but three of those ways are dead giveaways. They're totally reliable ways to tell if there's more disorder or order happening with the system. Okay, so number one is if it's a physical change or a phase change. Four ways to tell the sign of delta S cis. Okay, so if it's a physical change or a phase change. So, for example, if you have a solid that melts, a solid that goes to a liquid, what just happened? So we have a lot of order in the solid, okay, and then it just became a liquid. So more heat came in to the system, causing the molecules to move more and vibrate more. So what do you think that does to the amount of order? That's going to be more disorder. So that would be a positive delta S cis if that happened. Okay, and the reverse of that is also true. So if you have, let's say, a gas that condensed that went to a liquid, that's way more order that just happened. So that would be a negative entropy, change in entropy, if that happened. Okay, so phase changes should be real easy to tell what's going to happen on a phase change. Okay, the second way to tell is mixing. This one is a dead giveaway, that one there. Okay, so mixing. So most dissolving, and we'll come across a few that are actually become more ordered when they dissolve compared to the lattice crystal. That's really rare, but it does happen. So, but most dissolving processes, for example, sodium chloride, if it's a solid and it forms its ions, its aqueous ions. Okay, this is going to create more order on this side. I'm sorry, more disorder. Just more order. Okay. So most mixing processes are positive entropy because they create more disorder. Okay. Another one is gas formation. So watch out for gas formation, or if the number of gas molecules is reduced. So gas formation during a reaction. So for example, this one's huge. Okay, this one has a huge impact on entropy of the system. Okay, so for example, if you have, let's say, actually, let me just make it more general. So you can count the gas molecules on the reactant side and the product side and see if it decreased or increased. See if it decreased or increased. Okay, for example, if you have A plus B and it makes 3 molecules of C. Okay, we have 2 gas molecules on this side. So let's say the reacting ratio. I know this is not balanced, but 2 gas molecules on this side and 3 gas molecules on this side. Okay, we went from 2 gas molecules to 3. Okay, and if you start adding using grams and pressures to do this problem, you're talking about Avogadro's number if you're looking at the mole amounts. So if you have way more molecules of gas, this is huge increase in entropy or disorder. Okay, think about all those crazy gas molecules jumping around, slamming into one another, okay, causing chaos and disorder. So that's going to be huge entropy increase. Okay, and the reverse is also true. So let's say you had like 5 gas molecules. Let's say you had like 5A and 2B. Okay, and you created 1 molecule of C gas, or let's say they came together and made a solid. Okay, these 2 gas molecules came together and made a solid. So imagine that you started off with 7 gas molecules and it created a solid. So that would be a massive negative. That's creating a ton of order. Okay, so that would be huge. You should expect that number to be huge and negative for the amount of entropy change. Okay, for a reaction that did that. Okay. Okay, and the last way to tell, the fourth way to tell, and this one is I'm gonna put a note here and say that it's not always reliable. Okay, and we'll have to look at some examples like in class. We'll go over when it's reliable and unreliable. Okay, so but this is molecule complexity, and it's not, like I said, it's not always reliable. So molecule complexity. So for example, if you have like a molecule of H2 gas, which is this, okay, versus H2O. Okay, so H2O looks like that. Okay, remember that these molecules can turn around these. Okay, so they have this rotational energy, and then they also have translational energy. So the whole molecule can also turn around, okay, and spin. Okay, and the more bonds it has, typically the more it can rotate around. Okay, so this actually adds to the entropy. The entropy of H2O, so just by itself, you should expect it to be higher than the entropy of H2 because this can only rotate around this bond here. Again, it doesn't add to the amount of states or possible arrangements that it can do. So H2O has more, we could say it has more microstates. If you remember the concept from the last video, more microstates are available. So there's just more ways it can look. So that improves its amount of disorder in the molecule. Okay, so just be careful because this is really, I have found this is really only useful for when you're comparing like a couple of gas molecules. Because if you're comparing a gas molecule to like, let's say a solid, okay, like a solid block of sucrose, like table sugar, sucrose. Okay, this is like I believe C11H22O12. Okay, and you might think, oh, look at all those bonds it has. Okay, and so it's going to be spinning around all those bonds. Okay, this is not true because it's locked into place as a solid. Okay, and you might come to the conclusion that this has more entropy than this one, but it's not true because this is a solid and this one's a gas. So just by this being free of IMFs, it's going to have way more entropy than a locked together solid like that. So it's really only useful, I'll put a note here, I found it to be useful for comparing gas molecules. For comparing gas molecules of different types. Okay, so let's go ahead and apply these concepts to some situations. Okay, so here's the first situation I have is a forest fire. So we're going to try to address what the system is and what the surroundings are. And then we're going to try to ask, is this process spontaneous? Okay, so here's the second law. We have the entropy of the universe, and it's equal to the entropy of the system plus the entropy of the surroundings. Okay, and we're going to try to predict this sign and this sign to try and tell this sign of the universe. Okay, so for this, always remember that there's four ways to do it. So remember one of the four ways. There's four ways. So we're going to look at, is there a phase change? Is it a mixing process? Is there mixing going on? Are gas molecules forming? And lastly, is what about molecule complexity? Okay, and like I said, this one is not that reliable, that one. Okay, and then for the surroundings, we're gonna put it in terms of the system by setting this equal to its enthalpy, okay, which is dependent also on the temperature. Okay, and probably our next video will deal with this concept, how it's related to temperature. So, what is the system? The system is the chemical reaction. So trees burning in oxygen, making lots of lots of simple molecules. So we have solid. So we're actually looking at this one. This is the one that is applicable, is gas formation, because we're starting with solids. Okay, and then we're forming lots and lots and lots of gas molecules. So the system is always the chemical reaction. So in this unit, so the system, if you're ever wondering what the system is, think about this. It's always the chemical reaction. Always. Okay, so that's the system. So what is delta S for the system? Well, we had solid trees and they're forming gas molecules. So the entropy of the system should be a huge positive because there's more disorder. And if you ever get stuck on this, just ask yourself, is there more disorder or more order? Or more order here happening here. Okay, if you ever get stuck on entropy and answering that question. Okay, so what is the surroundings? The surroundings is everything else in this picture. Okay, that's not the trees and the oxygen. It's not the chemical reactions. It's everything else. So, and to look at that, we're going to look at this. So we know that this is a huge exothermic reaction. So the surrounding is the air plus other trees, etc. Okay, so what's delta S for the surroundings? So we're going to set delta S sur equal to negative delta H Rxn over T. Okay, and this we know is going to be a huge negative number because, well, it's creating fire. So this is going to have a negative and negative. So this is huge and positive, delta S sur. Okay, so is this process spontaneous? So is delta S universe increasing? Delta S cis plus delta S sur. Okay, well, we just determined that this number is positive and this number is positive. So, yes, this process is spontaneous at any temperature. Okay, you'll see that because of this temperature factor, can control the overall term. So you'll see that if this is high, it'll actually keep this term low, this entire term. But since it's going to be always positive, it doesn't matter. And this is always positive. So this is always positive. This is always positive regardless of the temperature. So this process will always be spontaneous no matter the temperature. Okay, so next we're going to look at one where we have a phase change. So this is a reduction sauce. And a reduction sauce is you're basically just boiling off the water from this. So you're making it more concentrated by boiling off water when you cook down a sauce, okay, and thicken it up. So you're causing the liquid to change into gas. So here we're looking at a phase change. So what's the system? It's the chemical reaction or process. The chemical reaction always or process. So what is the process? Chemical process happening? It's water being converted from liquid to gas. Okay. So what's delta S for this system? So we have liquid going to gas. We have liquid going to gas. So this is going from here, they're kind of close together and got some IMFs, to fully separated IMFs, okay, and lots of speed. Okay, more kinetic energy. So this is more disorder is being created. So delta S cis. So again, to keep consistent with the previous slide, we have delta S universe, delta S cis, plus delta S sur. Okay, and cis, we want to look at those 4 ways. Out of those 4 ways, we want to look at the phase change way. You should always be able to tell delta S cis by if it's a phase change. So this is more disorder is happening here. Okay, so what's the surroundings? Everything else. Okay, this is actually, so delta S sur, to figure out this, look at the 4 ways. To figure out sur, look at the enthalpy of the reaction or the phase change. Okay, so delta S sur, just make it super concrete, write out the equation and analyze and begin to analyze. So this was not a reaction as a phase change, but for this process, it's actually the vaporization value for water. Okay, so to look at this, we have to ask the question, what was the phase change? Went from liquid to gas. So you have to answer the question, does this require heat? Or does it take in heat? Sorry, I just asked the same question. Does this give off heat? This process? Or does it take in heat? It needs to take in heat. For liquid to turn into gas, it needs to take in heat for this to happen. Okay, so if it takes in heat, that is an endothermic process if it takes in heat. What is the sign for delta H for endo processes? The sign for delta H is positive. Okay, so we'll be putting a positive value here, but this negative makes the term negative. Okay, so the entropy of the surroundings is more order. It's actually negative. So is this process spontaneous? So we write out our equation, delta S universe equals delta S system plus delta S sur. This is an interesting result. So this one is the entropy of the system is increasing, okay, which is favorable for it being spontaneous. However, this is negative. So how do we tell the sign of universe? It depends on temperature, this process here. So I'm going to write this process, and this term needs to win. It needs to beat this term. So how do I keep this term small? How do I keep this term small? How do I make it lose against the positive entropy of the system? How do I keep it small? Well, look at this right here. I need a high temperature. So this is spontaneous at high temperatures, which makes sense. It needs to boil. Okay, so you could actually calculate the temperature at which it will be spontaneous. It happens to be the boiling point, 100 degrees Celsius for water. Okay, so this is spontaneous only at high temperatures, this process. Okay, so and you could actually use this formula and calculate that temperature if you know that the enthalpy of vaporization for water, then you can calculate the temperature. It happens to be the boiling point. So, and don't worry, in class we're gonna look at tons and tons of examples. We'll get used to doing this because it's predicting when a process is spontaneous or not. Okay, so now finally to the your turn questions. So I have this one. So this one you're predicting the sign of delta S for each of the following changes. So pay attention to remember that you want to look at one of those four ways. For delta S, look at one of the four ways. So is it a phase change? Is there mixing? Is mixing happening? Is something dissolving? Okay. Next, is it check the gas formation? Okay, did gas molecules form or did they go away from left to right, from reactant to product? Okay, and then check the molecule complexity. Okay, and I put a word of caution on this one. I said this is really only useful for comparing two gas molecules. Then it's useful for that. I found it's kind of confuses you actually when it's you're comparing solids. So okay, so try that, and then try this one. I also have this question. This one's more similar to the ones that I just did. So for all of these, you want to use this formula, the second law, and try to predict the sign of delta S universe. Okay, by trying to predict this sign and the entropy of the surroundings, those two signs. Okay, so that's the end of our video. Big topic, huge topic. This actually covers almost the entire unit, this one video. So kind of a long video, but it covers a lot of ground that you'll need to know. The rest of this unit, we're just going to be applying these to chemical reactions and actually like calculating values here. Okay, and then there's one more kind of big topic. It's free energy, but free energy is really just a way to put the entropy of the universe in terms of the system. So it's really just an extension of this video.